Hello everyone and welcome to this lecture. In the last lecture we derived a very nice result which tells that diameter is strictly lesser than the number of distinct eigenvalues of the adjacency matrix of a graph. Okay. In this lecture we will try to calculate the eigenvalue of some of the well-known graphs, and we call the set of eigenvalues as spectra also. So spectra of these well-known graphs. Okay. But before that, I need a help of when result that result actually relates the rank of matrix and the number of non-zero eigenvalues, and we are considering here the adjacency matrix. In fact, this result is true for any symmetric matrix. So let me first prove that result. Okay, the result is first of all this. So the result is, suppose we have a symmetric matrix. For a symmetric matrix, symmetric matrix, the rank for a symmetric matrix M, the rank M equals to the number of non-zero eigenvalues. Very neat result. Okay, let us try to prove this. Why this is true? For any symmetric matrix, rank is equal to number of its non-zero eigenvalues. Okay, let us prove it. Again, the spectral theorem will help us. Okay, so what was the spectral theorem? But before that, I think before making use of the spectral theorem, let us prove, or let us see one observation. Suppose A is some matrix of type BC which can be decomposed into B and C. Suppose A equal to BC, right? What can you say about the rank of A, rank of B and rank of C? Firstly, we will see that the rank of A is always, it can be at most minimum of rank of B comma rank of C. Why this happens? Why this happens? And by the way, this is for any matrix, any matrix. Any matrix, it need not to be symmetric matrix. We will make use of, let us see, let me write claim, this is a claim, if, okay, any matrix, right, then this, and we will make use of this claim. Okay, why this is true? Why this is true? Okay, see, suppose, I mean, this you can prove in many ways, but the simplest way that I can see is, suppose some vector is in null space of C. Okay, some vector x in null space of C, basically Cx is equal to 0. This also implies that Ax is equal to 0, right, just by matrix product. That means if x is in null space of C, that x is also in the null space of A, right? So nullity of C will be, so nullity of A will be at least the nullity of C, right, which by rank nullity theorem tells that the rank of A will be at most the rank of C. Okay, this implies rank of A is always less or equal to rank of, I'm again and again rank of C, right? Very good. This follows from rank nullity theorem. Okay. Now, in the similar way, if you take the left null space of B, if you take the left null space of B, that null vector, left null vector, whatever you say, is also left null vector of A, right? Okay. And in a similar way, we can prove that, we can derive that the rank of using rank nullity theorem, but of the basically left rank nullity theorem, whatever you say. Yeah. So rank of A will be nothing but at most rank of B. So this implies that rank of A is always less or equal to minimum of rank of B comma rank of C. Okay, very simple result. Okay, very good. Now how we can use this result for our purpose? Okay, so let us try to prove our main theorem. Okay, now I said that the spectral theorem again will help us, right? So what is the spectral theorem? So now A is our symmetric matrix, or maybe I have taken M here. Yeah, M. So M can be written as V D V transpose, where V is set of basically eigenvector which are orthogonal to each other. Okay, D consists of all the eigenvalues. Okay, so what about the rank of M? Let us see. Rank of M will be, if you see it clearly, I can write this as using this result minimum of, I mean if you expand this, it is not very difficult to see, it will be rank of V, rank of D, comma rank of V transpose, which is same, right? Rank of V and V transpose. So this is very simple. So let me actually erase it. No need to write it. And yeah, where is my? Okay, sorry. This is pen. Yeah. Now rank of V is what? Rank of V is what? Full rank. In fact, I don't think maybe it matters or not, maybe it matters later on, but I can see that from here rank of M is less or equal to rank of D. That much I can write. Okay, maybe you can put bracket here. Okay. Now you can also write the same thing. Yeah, now here I will. The same thing as basically this. If you multiply on V transpose both and sides, so V transpose M V equal to D. All right. Now apply the same thing. So what you will get is this rank of D. Now this you can do, but just why you can do it? Because V is set of orthogonal vectors, so the V is basically V transpose into V equal to identity, right? So you can always multiply this side, so no issue here. Okay, very good. So now yeah, so now rank of here again, if you do the same thing here from the above, in fact, yeah. So rank of D will be always less or equal to rank of M, and using these two we conclude that rank of M is indeed equal to rank of D. Okay. Now what is D? D is nothing but this, right? Rank, let me write, D is this matrix where there are diagonals, on the diagonal there are eigenvalues lambda 1, lambda 2 up to lambda n. Okay. So whenever there are zeros, right? So suppose last zeros. So basically rank of this is nothing but the number of non-zero, the rest of place is 0. The rank only depends upon the number of, basically the rank of this matrix is nothing but number of non-zero eigenvalues. So has this result follows. Okay, not very difficult to see. So I hope the proof is very straightforward here. Okay, great. Now let us find the eigenvalues, sum of well-known matrices. Okay, and as there will be some of DIYs also. Okay, so first very simplest kind of matrix is what? All, I mean complete graph, not matrix I would say, I mean we want to find the eigenvalues of graphs, right? So let us take first case of complete graph. What will be the eigenvalues of complete graph? Complete graph. Okay. So what is a complete graph? Complete graph, suppose graph on n node. So the complete graph is nothing but, so suppose these are the 5 nodes here. Complete graph is a graph where every node or vertex is connected to every other vertex. So for example here, Okay, I hope I have drawn all the edges. No, something is missing. Yeah, very good. So this is a K5. We can denote. We have seen it earlier also. There are 5 nodes. Okay. In general, so how the adjacency matrix will look like? Adjacency matrix will be looking like this. So there will be A will be something like, on diagonals there will be 0 zeros. Okay. Otherwise, everywhere this is 1. Everywhere this is 1. So this we can write as this. So this is n cross n. So this I can write as all one matrix, full one, okay, minus identity matrix, right. Now if I can find the eigenvalues of Jn, I can actually find the eigen of Gn minus I. Why it is so? It is so because, so let me write it as separately here. Suppose A equal to some basically if you know the Ax is equal to lambda x, okay, then so basically lambda is eigenvalue of A, then what will be the eigenvalue of A minus I? It will be nothing but lambda minus 1. The reason is this: if you multiply x with this, so this will give you what? Ax minus x, right, which is nothing but lambda x, okay, minus x, which you can write lambda minus 1 times x. Basically this is a vector, x is a vector, x is an eigenvector of A minus lambda A minus I, and the corresponding eigenvalue is lambda minus 1. So lambda minus 1 is the eigenvalue of A minus I, okay. So in the same way, if you can find the eigenvalues of Jn, I can find the eigenvalue of Jn minus I, that means of A, okay, very good. So let us try to prove this. So what are the eigenvalues of? So eigenvalues of, so eigenvalues of Jn, okay. So what are these? So how the matrix will look? Jn is nothing but this matrix, right? Okay. Now immediately, because it's a very fresh in our mind, we can see that there will be just one non-zero eigenvalue of this matrix. Why? The reason is because the rank of this matrix is 1. Rank is equal to number of non-zero eigenvalues when the matrix is symmetric, and this is symmetric matrix. So suppose this eigenvalue is lambda, so there is just one non-zero eigenvalue. Other eigenvalues are 0, 0, 0, 0, 0, 0, because there has to be n eigenvalues. So rest of the n minus 1 eigenvalues are 0. Okay. So yeah, but what will be that? What will be that? Again, the spectral theorem come help us in rescue. I mean, remember we have proven that the trace of the matrix is equal to the sum of eigenvalues. Okay. Now here there is just one non-zero eigenvalue, rest of the eigenvalues are 0. So in fact equal to trace, right? A trace is nothing but n here, right? Okay. So there is just one non-zero eigenvalue which is equal to n, and rest of the eigenvalues are 0. So basically let me write. So eigenvalues are 1, then 0, 0, 0, 0. So this is up to n minus 1 times. So multiplicity of zeros is n minus 1. Now it is easy to follow what will be the eigenvalues of A. We have seen that A is nothing but, so I can write this adjacency matrix of complete graphs is nothing but this, and so this implies that because the eigenvalues of this are this, so eigenvalues of A, or you can call a spectra of AK n is equal to this. So n minus 1, because I have to reduce this, and then minus 1 up to minus 1. This is with multiplicity 1, this is with multiplicity n minus 1. Very simple, right? Great. Okay, so I hope, I mean, you have seen, I mean, this result was directly visible from this rank, I mean, this above result. Now we will again use this result in proving, in finding the eigenvalues of some different graph. Now the different graph is this: complete bipartite graph. Complete bipartite graph. So what is complete bipartite graph? So again, definition is very easy. We have maybe have seen in the first or second lecture. So there are vertices here, and every vertex is connected to every vertex of other set. Okay, so like this. So this is, I hope anyway this will be very clumsy. So complete graph, complete bipartite graph. So suppose there are p nodes here, there are q nodes here. So this we denote by kpq. Okay, and how many edges will be there? There will be p into q edges, right? Very simple topology. Basically, the number of edges is p into q. Now, how its adjacency matrix look like? Adjacency matrix will look like. So if you see that. Okay, so adjacency matrix of kpq is nothing but, if you draw here, so suppose in this I have noticed all the vectors of the left hand side and this is the right hand side. So this side, I mean this will be fully 0 because there is no connection among itself. So there will be only connections here, right? So let me write this part here. So this will be, if you see that this vertex is connected to every vertex here, so this will all 1. Let me put 1. So everywhere this is 1. So all 1 basically, right? And this size will be what? I mean p cross q, right? So let me call it jpq. Okay. Similarly, in fact this is symmetric matrix, so opposite will also be true. So this will be all 1 matrix again, right? All 1 dot and let me write. Okay, and this will be 0. Okay, so again this will be, and this, what will be the size of this? This will be jqp. Okay, now how to find its eigenvalue? Again, let us see the first theorem, first result we have seen in this lecture. What will be the rank of this matrix? Rank of this matrix is 2, very visible, right? So there will be 2 non-zero eigenvalues. So suppose these are lambda 1 and lambda 2. Rest of the eigenvalues are 0. But what are these 2 eigenvalues? How can we find? Oh great, one thing is for sure, the sum of these eigenvalues is nothing but 0, which will imply that they are negative of each other, right? But do we require some more thing? But still we have to find the values, right? Fortunately, again the spectral theorem will, the result from the spectral theorem about the number of closed walks, okay, so that will help us. And we have seen that in the last lecture, we have seen that in fact that if you square the eigenvalue, take their sum. So right now here only there are 2 non-zero eigenvalues, rest of the eigenvalues are 0. So this will be nothing but twice the number of edges, right? So twice the number of edges, and number of edges here is pq. So this will be equal to pq. Okay. Now since from the first lambda 1 is equal to minus lambda 1, so this can implies that twice of lambda 1 square is equal to twice of pq. That means lambda 1 is equal to plus minus pq. Okay. So there will be only 2 eigenvalues. There will be only 2 eigenvalues. Two non-zero eigenvalues. So one is pq, another one will be minus pq, and rest of these eigenvalues are 0. Okay. So how many times this will be coming? This will be coming p plus q minus 2 times, because 2 is consumed by this. Okay. So I hope these 2 results are very easy. Now DIY. Okay. Now DIY. So there are several DIYs here, and very easy to say. Find the eigenvalues of Cs. Find the spectra or eigenvalues of cycle graph on n nodes, then path on n node. Path is just right a tree where every vertex has degree, only 2 vertex at degree 1 and rest of the has 2, right, unconnected. Okay, so basic, yeah, anyway, path you already know, no need to write. Yeah, okay. Then find the eigenvectors of Kn and Kpq. Okay. So with this, I am stopping this lecture, very short lecture, and see you in the next lecture. Okay.